So we are going to be discovering the aerodynamics of coffee filters today. They're going to act as parachutes. You should have with your group 8 filters all together that'll be just all embedded inside of each other. And you're going to be working with them, dropping them from different heights, finding the time it takes to fall, and then basically really looking for the air resistance from them. And I'm going to be kind of walking you through what you're going to be working with along the way. So here's our actual lab. So a couple things about it. You're going to be given 8 coffee filters. You're going to need your stopwatch on your phone and a meter stick to measure some heights. First of all, you're going to be measuring basically 2 heights. So the same person's going to be dropping the coffee filters. One you'll be dropping from the ground, and you'll just basically push your arm straight out away from your body. Don't put it above or below, somewhere where you're just comfortable. It's going to be the same height every time. Have somebody measure that height and go ahead and put it right here. Hopefully it's going to be, bigger than 1.5 meters, but if it's just below that, it's fine. And then we're going to be also dropping it from a chair. So you're going to have that same person go ahead and stand on a chair, push their arm out in front, measure the height of that one as well. So we're dropping it from 2 different heights. Basically from there, we will definitely have enough distance to have that coffee filter hit the terminal velocity. That hits the terminal velocity pretty quickly. Make sure that when you're dropping the actual coffee filters, you're dropping them from the bottom side down. So it's going to be falling this way. Do not have it the other direction. This way it's going to be teetering all over the place. So you're going to want it to fall this way, and it'll fall pretty nice and smoothly as it goes down towards the ground. When you're dropping it, please don't throw it up or down. Just let it fall. And you're going to be working with each one 2 different trials. So trial 1 is just on the normal ground. Trial 2 is when you're basically standing on the chair. You'll be dropping 1 filter from the ground, and then you'll drop that same filter from the chair. Basically, I would probably go ahead and do it from the ground first, then put it in the chair, and then what you're going to do is you're going to put 2 filters together. So make sure when you're putting these 2 filters together that they actually line up inside one another, so that way it just doesn't kind of fall apart. And again, you'll drop 2 filters from the ground, and then from basically the chair. And you'll do that with 4 filters, 6 filters, and 8 filters. And then from there, we will find out the velocity of the filter as it falls from your hand to the ground. So for example, let's say that it took 2 seconds to fall when I was standing on the ground, and when I was in the chair, it took 3 seconds. All right. And then my actual distance is, let's say that I was actually 1.5 meters from the ground on that one, and I was 2 meters when I was on the chair. Again, I'm just making up numbers here. You're going to be finding your velocity. This velocity actually will be your terminal velocity, the average velocity. So velocity, we learned a long time ago, is distance divided by time. So for example, if I want my initial velocity on the first trial, I dropped it from a height of 1.5 meters, and it took 2 seconds to hit the ground. So the velocity will end up being 0.75 meters per second for that one. And then basically we'll have the same one, but I dropped it from 2 meters for trial 2. So now the distance is 2, and it took 3 seconds to hit the ground. And so the velocity for that one will be 0.67, let's say. So we've got our 2 different velocities. They should be pretty much around the same because again, it's going to hit that terminal velocity pretty quickly. And that's one of the things we're going to be taking a look at is, do we pretty much have around the same velocities depending upon how many at the different heights. And then the big question will be is, are these same velocities going to show up when there's 2 filters together, 4 filters, or will the speeds get faster? Will the terminal speeds get slower? That'll be basically part of our actual project as to what we're trying to find out from here. From there, we're going to need to find out our mass. So basically, the easiest way to do this is actually measure the mass of all 8 filters together, and then you can go ahead and find that. Let's say it was 80 grams, and you'll just measure it with my scales around the room. So all 8 filters, let's say 80 grams. 1 filter, well, 80 grams divided by all 8 would be 10 grams each, so 10 grams would be that guy right there. And so that's basically what 1 filter more or less would be. From there, you will go ahead and plug in your different masses. Now we're going to be going to kilograms. So make sure you divide this by 1,000. So really that would be 0.1201 kilograms. And then you're going to find out, okay, what's the mass for every single one of these? Make sure they're in kilograms. So one filter would be 0.01 kilograms, 2 filters would be 0.02 kilograms, 4 filters 0.04 kilograms, whatever that might be. Again, I'm making up numbers here. So I'm just going to find a bunch of masses, again, measure with my scales. And then lastly, we're going to find the average velocity from trials 1 and 2. So you're going to take these two with the one filter, average them together. So if you want your average, we're going to be doing the 0.75 in my case, plus the 0.67, and then dividing that by 2. So 0.75 for me, plus the 0.67, and dividing that by 2, I end up with an average speed for one filter of the two different heights of 0.71 meters per second. Okay. From there, you'll do the same exact thing for the other ones. And again, I'll explain what this little darker box is when it's all said and done. So finding all your masses, finding your average speeds from the original table. So average speed with 2 filters, average speed for 4 filters, and then average speed with 6 filters, and so on. So that's the first one, and again, you definitely have a lot of room for your work over here on the side, so definitely be showing work. That's going to be worth some points along the way. Now we'll go ahead and start moving into the potential energy that these guys had. So finding the total potential energy due to gravity of the 8 filters. So we're working with just the 8 at this point in time. And potential energy is mass times gravity times height. So for mine, for the mass, we would have to go back again to the front. We want all 8 filters. So for mine, they were 0.08 kilograms. So I would say that I've got 0.08 kilograms in mass for all 8 filters, gravity 9.8. And we're dropping from a height of, well, we got 2 different heights. We got the 1.5 and the 2. So 1.5, I'll just do that one only for scenario 1. And I'll go ahead and find my potential energy for 8 filters dropped from the ground height. That is 1.176 joules. So that's how much potential energy we'll have. From the higher height on the chair, we'll definitely have a little bit more joules, maybe all the way up to 2 joules for that one, and go from there. Next, what we're going to do is we're going to use this potential energy to determine how fast should that coffee filter actually be traveling when it hits the ground, when all that potential energy due to gravity is converted into kinetic energy as it hits the ground. So basically, we already have the MGH 1.176 equals 1/2 the mass of the 8 filters, 0.08, times your velocity being squared. So basically, just a little bit of algebra for mine. Half of 0.08 would be 0.04 v squared, and then I'll go ahead and divide 1.176 divided by the 0.04. And my velocity squared will be 29.4, and then square root that, and I have a velocity of 5.42. So that's how fast the coffee filter should have been traveling if 100% of all the potential energy due to gravity is converted to kinetic energy. And then you'll go ahead and find the secondary one as well. How much kinetic energy did the 8 filters have when they actually hit the ground? Use the velocity from the shaded box from table 1. So if you go back over here, we have a velocity of how fast was it going in the end. So basically you will use this speed to go ahead and calculate how fast it was actually, how much kinetic energy did it actually have from the front with the velocity. So this is how much kinetic energy it actually did have. And the question will be is, was the kinetic energy that it had previously, 1.176 or whatever you have, did all that energy get converted to kinetic, or did we lose some? Let's say, for example, the kinetic energy was only 1 joule, okay, in the end. Well, I was supposed to have 1.176, but I only had 1, so if I subtract those two from one another, I'll find out that I lost 0.176 joules of energy to, most likely, air resistance, air friction, heat, as the little guy was traveling from your hand down to the floor. So most likely you're going to have less kinetic energy here then you will have potential energy up there unless something very strange happens. All right, so let's take a look at the next section. All right, so we actually looked at this formula when we were dealing with air resistance and such. Force due to drag, or air resistance, follows this formula in aerodynamics of 1/2 rho, that's the density of air, times the coefficient of drag, times the area of the actual parachute, or in this case, the coffee filter, times the speed that it's traveling at. That will actually be your force due to drag, or your air resistance force. So we'll actually be able to work with that. Air density for here at basically 0. We're not up in the hills. We're not down in deep valley. Air density, we're going to use 1.225, so you're going to actually have rho. Coefficient of drag for a coffee filter, I looked it up, and it came out to be 1.12. Surface area is actually what you're going to be calculating, and velocity is actually something that you already know based upon the velocities that you received from the front side of this paper. So you're going to basically be working with this formula to find the area of the actual coffee filter. So the big question is this: is the area due to air resistance going to be the flat surface that basically is traveling towards the ground, or will the air resistance be this edge corner, or will it be a combination of both? So we're going to be actually trying to find that out for the rest of this lab here. So let's go ahead and I'll do an example again for just one of the coffee filters here. So basically our force due to drag is going to be equal to, another name for it, is going to be weight. Well, here's the reality. When we hit terminal velocity, we've seen this before, your weight of the actual air coffee filter in this case is going to be equal to your force due to air resistance, because the sum of all these forces is going to have to equal 0, because this thing is at terminal velocity, meaning that your acceleration is going to be 0, which means our velocity is constant. That's the whole idea of what it means to be traveling at terminal velocity. So we're going to be able to actually know our force due to drag, because it's going to equal the weight, and the weight of these coffee filters is going to be mass times gravity. And you know your mass, you measured it earlier on with the scales. So we got mass, we got gravity, we got the density of air given us. I gave you the coefficient of drag, air, the area, we're going to be looking for that, and the speed, you guys calculated that earlier on. So we're going to be doing this, I'll do this one for one coffee filter to start. So for one coffee filter, the mass, earlier on I said mine was 0.01 kilograms, and gravity 9.8, 1/2 rho 1.225, again I'm giving you that, and coefficient of drag 1.12 gave you that. The area, don't know, and the velocity, let's see here, the velocity that I came up with was 0.71 for the single filter, so 0.71 meters per second. 0.71. Do not forget to square that, velocity being squared. All right, so we definitely have some number crunching to do. 0.01 on the left times 9.8. Just going to move that decimal place over a little bit. 0.098. 1/2, 0.5 times 1.225 times 1.12 times your 0.71 squared. For me, worked out to be 0.3458 times the area. So I'll go ahead and just divide that in. So the area, 0.098 divided by 0.3458 is going to be an area of 0.283. And again, this is going to be in meters squared. So it seems pretty small, but a meter is pretty large. And again, so this is all in meters squared. Again, I'm not saying that's the answer. You will actually have a surface area much smaller than that. But again, I just made up some numbers, so that's basically what I have. I'll do that again with two coffee filters, so the mass will go up. The air density will stay the same. The coefficient of drag will stay the same. Your speed probably will either go up or down, or maybe stay the same, but you're going to be, again, pulling that from the front table, your average velocity for the two filters. All right, so you're going to find all your areas, and then I'm going to want you to find your total average area. So we'll combine all these areas together, find the average. All right, lastly, we're gonna actually be looking at actual areas. So what you're gonna do is you're gonna take your coffee filter and kind of flatten it out here. And you're gonna be finding a couple diameters. So we're gonna be doing the diameter of the bottom of the filter, so the inside, and then we will actually do the complete full coffee filter as well. So we're gonna measure diameter because it's a little easier to measure the diameter, and then we just cut it half for the radius. Make sure you're measuring these things in centimeters. So basically, you know, mine's around 8-ish. I'm just gonna say 8, but it's not exactly 8. So I will just say 8 centimeters. The radius is half the diameter, so that drops it down to 4 centimeters. So basically that will imply that my area is gonna be, and then you're just gonna use your formula for the area of a circle, pi r squared. So pi r squared. But if you take a look, when we're comparing up these areas, this area is in meters squared. This is all in centimeters squared so far. So actually what you're gonna wanna do is switch this over to meters. So divide by 100. So that would be like around 0.04 meters. And let's go ahead and find the area, not in centimeters, change this to meters, because otherwise you can't compare the two. So change your centimeters into meters, use this when you're finding your area. So mine would be pi times 0.04 squared. And again, this is not the actual area, but it'll be kind of close to it. Pi 3.14 times the 0.04 squared. Area basically about 0.005 meters squared. That's for the inside. And then you'll do the same thing, but you'll measure the diameter of the whole entire thing. And do that again here. Make sure you switch your centimeters into meters. And then make sure you go ahead and find the area meters squared. So you've got two different areas at this point. One, just the bottom portion, or two, the whole entire filter. What you're gonna do is compare these values to your average area in the front up here, and then answer the questions as to which one seemed a little bit more appropriate. You'll go ahead and find some percent errors, and then just answer a few of these questions. On the back side, we have just kind of like a final conclusions regarding just air resistance and what would happen if we were to drop these things from different places on Earth or on the moon and such, and just making sure you truly understand actually what this is all about in the first place. So hope that your group does well. Hope this was interesting, and please by all means ask me any questions during class if something didn't quite make sense of what I said in this video. All right, good luck. Looking forward to seeing how you guys do. Take care.